The work I'm going to share today is joint with a former master's student of mine, Toby Harvey, and then my long-term collaborator, Jeremy Cosden, who is now left academia for an HPC company, and then my other PhD student, Alexander Chen. So much of the work today is going to be work that they largely conducted. I wanted to talk first about the larger scope of our group's work, and that's in high performance numerical methods for earthquake sequences on geometrically rough faults. This is some funding we've gotten recently. We proposed some work in light of some recent earthquakes that nucleated on faults thought to be unfavorable to the remote stress field, and then cascaded through large fault networks and involve multiple faults. And some of the questions we want to answer are why some earthquakes nucleate on faults thought to be unfavorably oriented, and under what conditions can system-wide earthquake ruptures occur in these networks. This is a larger picture for our work in terms of developing physically robust forward models. This it's a flow chart here, and we've largely remained over in the right, like the lower right corner of this, where we've been focused on applied math side of things and developing high performance computing techniques. Sorry, I'm going to move this because I can't see my own slides. Okay. And I share this slide only because, we're sort of looking to expand our group and bringing in more students and postdocs that will help us flesh out the other corners of this flowchart in terms of taking our model outputs and making connections to observables, refining our understanding of parameters and parameter values. And then I put question marks all over the slide, even in the corner where I said we did most of our work, because as it turns out, can spend a lifetime studying AX equals B and still not really have a good solution for every single type of scenario. Let's see, okay. Our computational framework and methods. So we develop methods based on the SBP stat finite difference methods, which are similar to certain types of finite element methods. We can do complex geometries and material and frictional heterogeneities, bulk and elasticity. And our recent target has been the earthquake cycle with full dynamics. So we've been developing robust numerical methods for the wave equation in second order form, connecting these to our inner seismic solver methods, and then switching between the two. We've been using, we developed recently a second order, a method for the second order wave equation with rate and state friction that effectively removes the numerical stiffness from the formulation and enables us to use general time stepping methods, explicit time stepping methods. And that's in our recent JSD paper with these figures down here, where we looked at the elastodynamic wave equation in 2 dimensions with various irregular fault geometries. For example, the green circle here is a nonlinear fault. And then we chopped up our domain into different computational blocks. We've been able to explore material heterogeneities in some of the figures down here. We looked at the anisotropic wave equation. We've been looking at applications to earthquake sequences with full dynamics, which I'll talk about today. And that's some work involving exploration of the effects of sedimentary basins. And then we've been working to advance our code for HPC capabilities in terms of the dynamic and the inner seismic solvers. So I say quasi-dynamic, quasi-static, which is another conversation. But in any case, we're interested in enabling our work to be able to do to perform the sparse matrix vector product in an efficient manner, and also looking into iterative methods and their associated preconditioning. So I decided to share some of the developments for our non-stiff method through some more simple examples than what we have in the paper, just because the notation can be kind of heinous. And I like to describe the SBP SAT methods that involve weak enforcement of boundary conditions by looking at a prototype problem, which is the 1D advection equation or transpro problem, which is given by equation 2 on the domain from 0 to 1. It has some initial condition given by G of T that determines information that flows into the domain. Discretization of 2 in space is given in the lower right corner here. Where D is a matrix approximating the first derivative, H is the grid spacing, E0 is the first basis vector in Rn, and U0 is the numerical solution at the left grid point, and U0 star is a target or numerical flux value, which we take to be equal to the boundary data. So what this effectively does is this term on the right-hand side of the discretization penalizes the first equation in this now system of differential equations, and it forces the numerical grid point there to relax towards the target value. So this is a movie I made where you can see the left-hand side is where the boundary condition is. The blue curve is the exact solution, and you can see that even at the left grid point, the numerical solution, which is shown in gray dots, sort of oscillates around that because it's imposed in a weak manner. So to illustrate the non-stiff method we derived in our recent JSC paper, I want to look at the elastodynamic wave equation, which is given here on the domain 0, 1. And I'm going to consider different boundary conditions, but I'm going to focus in on assuming we have a rate and state frictional fault at x equals 1, so the right boundary. And that I'm going to just write generically as tau equals f of u dot, which is the particle velocity, where tau is the boundary traction for normal vector n. I'm just going to assume for the sake of the illustration that f is, you can think of it as the frictional strength, but I'm going to assume it's just a linearized friction law with parameter alpha that determines the that determines the friction law here. So alpha is a positive, non-negative parameter that ranges over many orders of magnitude in a dynamic rupture simulation. So the idea here is that you want to be able to implement this boundary condition for various alpha that range over many orders of magnitude and try to not introduce numerical stiffness, which arises oftentimes in these types of problems. So boundary condition 3, where you have tau now equal to alpha u dot, I've inserted the friction law there. It can be rewritten as 4, which is u dot equals tau over alpha. And the only reason I do that is because you can sort of see now that different values of alpha determine different types of boundary conditions. So for example, if alpha equals 0, it's equivalent to enforcing a Neumann condition where tau is 0. And if alpha goes to positive infinity, it's equivalent to enforcing a condition on u dot or on velocity. So you want to think about the different limits as alpha goes to either 0 or infinity. And you can rewrite 4 or 3 in a characteristic manner where you write the incoming characteristic u dot plus tau as some reflection coefficient times the outgoing characteristic at that boundary. Now, R here is a reflection coefficient, but it can be related back to alpha by this ratio of 1 minus alpha over 1 plus alpha, and you can back out what alpha is related to R using this equation. And again, this corresponds to a non-negative alpha, but a reflection coefficient that varies between -1 and 1. And again, R can also specify different types of boundary conditions. For example, R equaling 0 corresponds to a non-reflecting boundary condition. So if you discretize the wave equation with the SBP SAT method, you get this first equation 6 down here where dxx approximates the second spatial derivative, and then you tack on 2 penalty vectors that enforce boundary conditions on either side. Since we're looking at enforcing a rate and state friction law on the right boundary, I'm going to focus on the very last ODE as part of this ODE system, which is UN double dot. The first term on the right of equation 7 is just it's a one-sided finite difference approximation to the second derivative at the right boundary. Then the next 2 terms are the 2 terms that impose the boundary condition at the right endpoint. Now, H again is the grid spacing, N is the normal vector, and Bn transpose approximates the first derivative at the right boundary. So in 7, the middle term basically takes a numerical approximation to the traction vector and penalizes it towards tau star, which is a numerical flux. And then the very far right term on equation 7 also penalizes the displacement at the right endpoint towards some target value UN star. And so these starred quantities are called these numerical fluxes, and they can be chosen to impose different types of boundary conditions. So I'll share a little bit more about this and then talk about the figure that's on these slides. The numerical fluxes. So for example, if you want to impose a Dirichlet condition, so a condition on displacement, you can choose a numerical flux for tau to be 0. and then just choose the flux for displacement to be the actual grid function evaluated there. Sorry, these should be ends. I sort of switched which boundary I wanted to look at. So this again is focusing on the right boundary. And then if you want to impose a friction law of the type we've been considering, where tau equals alpha u dot, the straightforward or non-characteristic approach would be to take these following two conditions for the numerical fluxes. So you take tau star to be alpha u dot and u star to be u. Again, those are just the grid points evaluated at those boundaries. So you can see actually now this is problematic choice for alpha going to infinity. Imposing something like this causes the system to have a very, very large negative eigenvalue as alpha approaches minus infinity. And that's the cause of numerical stiffness in these scenarios. So I put a box over here, and instead we choose to do a characteristic approach where the numerical fluxes are chosen to satisfy A, the friction law, and then B, they are chosen to maintain the outgoing characteristic. It seems a little bit odd, but one way of thinking about it is that it's equivalent to imposing a characteristic boundary condition in terms of a reflection coefficient R, and R now will vary from -1 to 1, and R is a ratio of different values of alpha, and it's always between -1 and 1, and so it never introduces an eigenvalue that moves towards minus infinity. So the figure up here on the right is, you can see alpha actually ranges over the top axis here as R goes from -1 to 1. And this traditional approach is in the red X's, and you can see that for R approaching -1, which is the limit of alpha going to infinity, the maximum real eigenvalue goes towards minus infinity. And it can see that it remains relatively stable for the characteristic imposition of that boundary condition. So one of the benefits of this is that it removes the stiffness and enables any explicit time stepping scheme. Otherwise, you would need to develop a specialized implicit scheme. We've demonstrated numerical stability and convergence, which is shown in the figures on the right, where we show up to 5th order spatial accuracy achieved for this characteristic boundary treatment. And then on the left is a figure of the Courant number associated with the explicit time stepping scheme. We use a low storage 4th order Runge-Kutta scheme during the coseismic phases. And we did our studies for a nonlinear friction law where f of v is proportional to this arc cinch of v. And then we looked at different proportionality constants beta, and you can actually see that as beta increases, the Courant number for the characteristic implementation remains constant, whereas it's like inversely proportional to the non-characteristic implementation, which tells you that you have to take a smaller and smaller time step with the non-characteristic implementation. So we've been looking at targeting our applications towards the effects of sediments. We wanted to revisit the quasi-dynamic simulations of Erickson and Dunham, which was some work I did as a postdoc, where we looked at earthquake cycles within sedimentary basins, but we only assumed a quasi-dynamic response. So we want to revisit this with full dynamics present. We're maintaining a view of the 2D antiplane problem with a vertical strike slip fault. We do various grid stretching from a physical domain to logical space so that we can use more or a smaller cell size near the fault and near the Earth's free surface, in this case, just for better resolution, for computational efficiency. We were looking at a sedimentary basin of depth D, and I'm going to focus on the original result where D was taken to be a 4-kilometer deep basin. And we have a decreased shear modulus within the basin. We use a rate and state frictional formulation with depth variable parameters in the aging law. And then we incorporate a switch between the sort of quasi-static or quasi-dynamic methodology where inertia is disregarded, and you switch to full dynamics once an event nucleates. And then once the event is over, you switch back to using the interseismic solver. So it involves like a switch of numerical methods. So this is just a proof of concept. It's a video I made, and it shows the event nucleating at around 8 kilometers depth or so, and it propagates upwards towards the sedimentary basin, and you can see that the associated shear wave speed is greatly reduced inside here, and it also shows some trapping of those waves inside the basin as they reflect off. So it's it's a sort of proof of concept that also I think illustrates some interesting numerical challenges in terms of like, when do you decide that the event is over and you've decided and you want to switch back to your interseismic solver. So you can see here, for example, we have non-reflecting boundary conditions at nearly all sides except for Earth's free surface, and that's during the coseismic phase. If I go back, you can see, I don't know if my pencil is showing up, but in the figure at the top, the boundary conditions on the left and right and at the bottom change depending on what regime you're on. So if you're in the interseismic phase and you're disregarding inertia, we impose slow tectonic loading at those lateral boundaries, and we make the lower boundary free. And when we switch to coseismic, all of those boundaries become non-reflecting. Go forward here. All right, so the switching criteria. So when do you switch, and when do you switch to your coseismic fully dynamic solver, and when do you switch back? So this has been a really interesting topic of conversation because we've been doing our first benchmark problem on these, and there's other participating codes that use a switch. Not all of them have to, but a lot of them do. And there's different groups that are switching based on maximum slip rate. For example, my group, there's a paper from Prithvi Thakur that came out in 2020. There's other groups that are also implementing a switching criteria, but it can be based on different things. For example, the work of Dewar et al., they switch based on a non-dimensional ratio of radiation damping to quasi-static shear stress. So we also explored switching on R, this non-dimensional ratio, and I think we just found that, we explored these for heterogeneous material properties and found that if you look at isolated events, for example, in the right figure over here, we plot in the insert max R over time. And you can show that if you switch at sort of later and later stages from the interseismic to the coseismic solver, you remain on this same curve. And so the different colors correspond to switching down here. So switching based on 5 millimeters per second being the maximum slip rate, 1 millimeter per second, or 0.5 millimeters per second. So I'm just saying that with these different choices of switching based on maximum slip velocity, we tend to remain on the same max R curve. And looking at that isolated event, it seems robust to that switch. And yet when you look at the long-term cycle simulation, you actually get divergence of these model results. And I say here that this is like largely due to the fact that for these heterogeneous problems, we're in a higher instability ratio, or that's sort of that was introduced by Lambert and Lapusta's 2021 paper that showed that if you're in the high instability ratio regime, you really tend to get long-term divergence regardless of your cell size used. So if you look back at the video I just showed that showed particle velocity, ideally we would like to switch actually based on maximum particle velocity rather than some field that exists on the fault. But we found that since our non-reflecting boundary conditions are not perfect, we tend to get reflected waves that sort of oscillate around for like a really long time, that are close to zero but don't decay. So we opted to switch based on max V on the fault, and ideally in future simulations we would add some form of artificial dissipation. There are other numerical issues. This is a snapshot of our paper that's in revision at BSSA. This is the SEEDS benchmark for our first fully dynamic problem, where it shows time series of shear stress and slip rate during a coseismic event in the cycle. And you can actually see this, that our code is Thrace, which is an orange, and you can see that there's a big step change when we switch from the coseismic to the interseismic solvers. So we opted to switch at around 15 seconds after the event nucleates here, and you can see there's a big step change. There's other codes here that are participating that also involve a switch that also contain a step change in the time series. They're just harder to see in this curve. But my point with this is that there is a step change in shear stress that occurs when you switch from the fully dynamic to the interseismic solvers, or coseismic to interseismic. And I don't think it'll ever go away. I think it manifests itself because of the fact that the equations, the quasi-static equations, are not the quasi-static limit of the fully dynamic equations. And largely that has to do with the change of boundary conditions that you assume from one regime to the other. The interesting thing, however, is that it seems to not affect the long-term features of the simulation, at least in the homogeneous problem explored in BP1FD. So even though these step changes exist, it doesn't really seem to greatly affect the recurrence intervals and other metrics that we've looked at in terms of long-term processes. So I'm not sure how I feel about that. And I don't know how to address it in the future, but I do know that the switching, criteria, at least for the heterogeneous problems, the results are very sensitive to that. So in terms of revisiting the studies of Erickson and Dunham in 2014, this is a figure from that paper, which explored the effects of sediments, where we just assumed quasi-dynamics for the meantime. So you can see in these cumulative slip profiles that there's a sedimentary basin that exists at 4 kilometers depth, and that's why you get the rupture greatly slows down when it hits that basin edge. In these quasi-dynamic simulations, we saw an alternating sequence of sub-basin and surface rupturing events. And these occurred when you had sufficiently deep or compliant basins, the sort of alternating switch. We sort of discussed in the paper insight into possible shallow slip deficit, or at least for observations of like buried ruptures. And so the question of being, how is slip accommodated during those in the long term, and we postulated that it might just be accommodated by part of a future surface rupturing event. There was a reviewer for this paper that suggested that perhaps with the inclusion of full dynamics, we would never see sub-basin ruptures, or at least that they would be harder to see. So now that it's been 8 years since then, we finally came back to exploring whether or not full dynamics, given everything else fixed, right? If you include full dynamics, would you not see these sub-basin events? So let's look at it. I have the quasi-dynamic simulation above and the fully dynamic below, and you can see that the alternating sequence still persists even with the presence of full dynamics. So in all of these cases, you can see that with full dynamics, you get much higher slip rates, you get more slip per event, and you also get an increase in rupture speeds. One of the interesting things is that, the presence of full dynamics does not sort of do away with these buried ruptures. We did explore what happens if you take a final snapshot of the solution after or sort of right before a sub-basin rupture, and you either send it to a quasi-dynamic or fully dynamic solver. And yes, with the full dynamics present, you can penetrate much, much farther into the sedimentary basin and actually propagate all the way through. So it's really a long-term feature of what are my initial conditions prior to rupture that dictate how far into the sedimentary region I can propagate. So over on the right here, I plot shear stress. Let's see, what do I do here? So the figure on the right, figure A, I plot fully dynamic and quasi-dynamic shear stress, and this is this is following a surface rupturing event, and that's A below. So what you can see that's interesting is that the shear stress for the fully dynamic simulation is a lot lower. So that is really what gives rise to the ability or the disability, I guess, for the next rupture to not penetrate all the way to the surface. And after that surface rupturing event, after the sub-basin rupture, you can see that there is a stress concentration in both scenarios that enable the next earthquake to propagate all the way through. So let me see how much time I have. 5 minutes or so. So we've developed a provably stable numerical method for the wave equation in second order form with a characteristic boundary treatment that removes the stiffness associated with rate and state friction. This does enable the use of a wider class of time stepping methods for earthquake rupture problems with nonlinear interfaces. We did hypothesize that the fully dynamic simulations would see an increased frequency of surface rupturing events, and yet the alternating sequences still persist even with full dynamics present. So these sub-basin events in the fully dynamic simulations were made possible by these previous surface rupturing events that left a reduced shear stress within the shallow basin. So in terms of rupture potential to penetrate into unfavorable regions, I said this already, but we did look at isolated events. So we initialized a quasi-dynamic simulation with initial conditions from a dynamic surface breaking rupture. And we find that the quasi-dynamic simulation cannot penetrate through the basin. So certainly with full dynamics present and given the same initial conditions, this dynamic rupture can propagate a lot further. But we just want to state that perhaps it's not enough to run a single dynamic rupture simulation in order to infer rupture potential into and through these regions that might be unfavorable to slip, but that it's really important to consider initial conditions left by a long history of seismic cycling. So all of our code for this was written in Julia and is publicly available here. So I'm just going to stop there because I am. And my email address is down here if you have questions.